Good morning. Thank you for joining us for prioritizing your data analytics work with Benfords Law. Kurt Johnson, the Manager of Solutions Development at Automation Services, the U.S. distributor of IDEA data analysis software, is going to demonstrate how IDEA uses advanced Benfords Law tests to help focus on critical areas to target your analysis. If you have any questions, you may enter them in the questions box on the right side of the screen. We will answer them at the end of the presentation. All right, let's get started. Kurt?
All right, hello everybody. Can everybody see my screen? I'm Kurt Johnson. I'm Manager of Solutions Development at Automation Services. And today we're going to be discussing the prioritizing of your data analytics work with Benfords Law. We're going to focus, we're not going to focus on any of the math of Benfords Law. We're going to focus strictly on application today. And what I'm looking to show you is how you can take analysis work that you've done for audit analytics and see about how you can prioritize what you should be looking at to best make use of your time to go after the most suspicious, risky kinds of transactions that you may have detected. So before we get into, so for Benford's Law, let's talk about what that is. Benford's Law, according to the ACFE, AICPA, and IIA, is used to determine and examine transactional data for unusual transactions, amounts, or patterns of activity. It's sometimes called the first digit law, and it's used to signal abnormal duplications that could be occurring in data. It's very useful for many naturally occurring data sets where the numbers have an expected relative frequency count for the digits of the numbers. So by that we mean, for a naturally occurring data set in nature or things where we've done counts of things without any artificial influence. We'll talk a little bit more about that later in a little bit. Where we're going to want to see, we can see a regular pattern that occurs based on certain digits for the numbers in the data sets. So in data sets in general that conform to Benford's Law, numbers starting with 1 occur 30% of the time, numbers starting with 2 almost 18% of the time, numbers starting with 3 would occur 12 to 13% of the time, and 4 would occur about almost 10% of the time, all the way on down to 9, which occurs about 4.5% of the time. Graphically speaking, Benford's Law gives you a logarithmic geometric kind of view where you can see the 30% for digits starting with 1, and then the 18% that start with 2, 3, etc. And what we're talking about here is we're talking about the numbers that we see and where these numbers occur in the actual, these digits occur in the number sequence. So we're looking to identify bins of digits with suspiciously high counts of transactions. And the traditional use of Benford's Law is to identify these bins of digits and then go audit them specifically as a group. We are looking examples of so we saw already the bins of first digits are simply the numbers 1 through 9. The first 2 digits bins could be 10, 11, 12, 13, which could in the 2-digit bin of 10 could be the number 10, the number 100, 101, 102, 1000, 1001. You get the picture. 1 million, because that starts with 10 as well. We have the first 3-digit bins. So again, you could have 100 and 101, 102, 103. Those all could be in separate different bins. Yes, they could have. All of these would be grouped under the 2-digit bin of 10, but we could also separate it out and look at a more discrete breakdown of bins if we were to look at, say, first 3 digits instead of first 2 digits. And the idea here traditionally has been there's likely something wrong with the items in the group that made the frequency counts of the transactions way higher than the Benford's law naturally expected for the accounts to be. So we're going to look at that application a little bit, but we're going to focus on two other applications today. And one application of Benford's law is to perform a quick initial assessment to see if the population, if it's supposed to conform to Benford's law, well, does it conform? Because because if it doesn't conform, and it should, there's an increased likelihood of fraud somewhere. You can use this to do a general prioritization of your work, as sort of like a health check, if you will, where you can go and say, okay, we have goods receipt, inventory, we have procurement invoices. We don't know exactly where to start and which area we should focus the most of our time. Well, if we were to perform Benford's law from a conformity aspect on inventory, the procurement invoices, the goods receipt, we would, if we found that one of those three did not conform and the other two did, then we'd probably choose to prioritize our analysis time on the one that did not conform. So this would be a way of being able to use Benford's law from an overarching standpoint to come up with a way of prioritizing where in general to start one's work. Now let's say you've picked invoices as part of your procurement to pay process that you wanted to focus on, and you perform data analytic techniques in there, such as duplicate testing, cross-matching and joining, and filtering of data to identify exceptions with these audit techniques to be able to have items to audit. What happens here is, at this point, how we're going to look, you have results that are available to you. And let's flip over and look at some examples where perhaps you're doing the work in Excel and you have looked to identify invoice duplicates. So here's an example of some invoice duplicates that we found, and we could find them in Excel perhaps using conditional formatting, or we could highlight cells, go to duplicate values, pick a format for the cells, and then provide some rules using countifs, functions, things of that nature to define exactly what we wanted to see in terms of detecting duplicates using formatting. And then we can extract that formatting out to get results such as these. This is where we're looking to see where we have the same vendor, invoice number, same invoice date and amount. And we found all these duplicates. The problem we have here is we've identified 34,000 of them in change. Which ones do you look at first? Well, one obvious place to look would be the biggest items. So that would be one way to prioritize your search. But there's no way you can look at all 34,000. So we're going to have to figure out a way to prioritize in some fashion, perhaps in addition to looking at the largest items. Also, if you did analysis where you're a VLOOKUP hero in Excel, and you were looking to see, okay, for a particular we have a certain vendor, we were able to match it up with certain P-card merchant names, and we wanted to find items with very similar amounts where the accounts payable description has some similarity to something that was in the P-card system, and we would like to be able to identify those items using some fancy VLOOKUP in Excel, and then at that point we have the same problem. We now have data from two different systems, the P-card system and the AP vendor system, and we have 344 items. How do we decide which items to go look at? Well, this is where Benford's law can come in. And what we're going to want to do is, we want to be able to prioritize our auditing of these exceptions using Benford's Law. And I'm going to show you how we can do that. We're going to look at some of the look at some of these first order tests, and we're going to utilize those to prioritize our results. So we have the first digit test, which is a test of conformity. That's usually too high a level to be of much use, but it's good for that second application, right? To see if the data conforms to what we expect, which might help in terms of picking a general area to start working in. The same for the second digit test. It's also a test for conformity and reasonableness, and that's too high a level to be of much use. The first digit test we already saw, where we look at the first digit of each number and categorize those in bins and look at the counts of them. With the second digit test, we're looking at the second digit in the number, and then we're looking to see what the pattern is for those. And it should follow the usual progression that we see in Benford's Law as well. In AP and AR data, it's very normal to get prices where zeros and fives tend to be higher than normal, and that is expected in those kinds of areas. We have the first two digits test, which we're going to focus on today, which is a good test to find spikes in counts that indicate abnormal duplication bias. A lot of times you'll want to look for spikes just under, say, two-digit bins for internal authorization levels to see if you have abnormal submissions right underneath those authorization levels. The first three digits test is basically, just for completion's sake, the first two digits test expanded to do 3 digits, and it can give you a finer breakdown. And you could use it in the manner in which I'm going to show you how we apply it here in IDEA. Okay, so I'm going to flip over to IDEA, and we have the actual data for, here's some accounts payable data, where we have your basic fields here of your invoice numbers, dates, amounts, and descriptions for particular vendors. We've identified similar merchants already that would be closely associated with the vendor name for the vendor. And what we're looking to do here is we want to be able to first, now we could, in Excel, you would do conditional formatting to get the duplicates. Here we can do duplicate key detection in IDEA, and fairly quickly do same vendor name, number, invoice number, date, and amount, and generate the duplicate results that quickly. You can see where that is a lot faster than having to do the conditional formatting and COUNTIF's rules. We still have the same issue though now, and we have 34,000 duplicates, and we want to be able to prioritize our search. So what we can do is we can go back to the AP data and perform Benford's Law on the invoice amount. We can create a result. So this is Benford for the webinar. And it'll give us the results like we saw in the PowerPoint for our first digit test. We have our second digit test where we can again see the 0 and the 5. Since this is AP data, it's not unusual to see bigger spikes on 0 and 5 like usual. We have the three digit test, which gives us breakdowns into much more discrete bins. And then we have the first two digits test, which we're going to use to be able to prioritize which duplicates to look at first. The cool thing about IDEA is it's going to break down the Benford's graph and the outliers into suspicious and highly suspicious bins. So the 6 bins that are most egregious in spikes are the ones that are highlighted. And you can see that we have highly suspicious bins where for numbers that start with 10, 25, 50. We have numbers that start with 20, 30, and 75 being and everything else as being suspicious. And so what we'd want to do now is see about how we can prioritize our search with the duplicates. And the way we'll do that is we'll come over here to our duplicates area, and we're going to append a field. We're going to append a field, and we'll call it the Benford rating. And we're going to come in here, and I've already prepared an equation. And this equation here, I'm going to take just a little bit of time to explain what we're doing here. But basically, it's saying, okay, let's first off do a complex if statement where we say, okay, if the invoice amount is greater than 1,000, so we're going to apply $1,000 or greater as a materiality threshold. And then we're going to come to the invoice amount, make it a string, and then we're going to use the left function to pull off the two leftmost digits from the string. And then we want to see if those two digits happen to match 10, 25, or 50, which we said were the highly suspicious bins. Those will be assigned a value of 2. If the invoice amount is again greater than the threshold, say, of $1,000, and the invoice amounts starting two digits are 20, 30, or 75, then we'll give it a value of 1. Otherwise, it gets a value of 0. And this allows us to input this Benford rating, and then we can index like so in IDEA, and quickly bring to the top the ones that are identified as the most highly suspicious bins with Benford's Law. We can see here we have those that start with 10 as being, and 25, and 50 being identified as some initial ones that we may want to go and take a look at. And we can see as we get down the list here, the ones that start with 30, 20, and 75 are also going to be in there until such time as and that would give us 161 of the duplicates to look at as a priority over the rest of the 34,000 duplicates that have been identified. So this is the general approach for being able to identify risk areas and to prioritize those using Benford's Law. The way we do the AP and P card match is in IDEA is we can come back to our AP data and we can run the visual connector. And we can run that on the P card data where we're going to take our merchants that we've matched based on fuzzy merchant name matches. And we'll call those AP P card many-to-many match. So what we're going to do is we're going to make a many-to-many match of the items between AP and P card. This gives us 134,000 records. And we want to be able to, now that we've done this, we want to be able to say we've matched based on vendor. We want to be able to match also on description. So we want to be able to see if this description in AP and these transaction descriptions from P card, how similar are they? And use those to be able to make our match. So what we'll do is we'll append another field, and we'll call this similarity description. With 5 decimals. And we have the ability to save equations in IDEA, and these are saved equations, where we're going to look at get a similarity rating based on Damerow-Levenstein distance between the AP descriptions and the P-card descriptions. Once we've done that, we can then see that we have the similarity ratings between those two. We also want to look at the difference in in transaction amounts. So we'll append another field, and we'll call it diff invoice tran amounts. And it's going to have 2 decimals. It's going to allow us to do we have an amounts percentage difference, where we can say, based on the invoice amount and the transaction amount, calculate the percentage difference using this formula. Once we've done that, it tells us what the percentage difference is between the different amounts, and it tells us what the similarity descriptions are. Once we've done that, we want to be able to say, well, we've found all these different combinations of matches, and we've evaluated the closeness of them all. Now what we want to do is we want to run direct extraction in IDEA to get to the APP card matches. And we're going to put in another equation. And this one is going to be called extract APP card matches. This is a judgment call, but we're going to basically look to see, give me all the similarities greater than 60%, and give me all the percentage differences less than 15%. When these are very subjective, but in this way we can then weed out the ones that are not close to each other and get down to a subset, like the one we saw in Excel, that we would have perhaps accomplished with some fancy VLOOKUP hero work. And then we can see now that we've identified those 344 transactions that you saw in Excel. Once we have that, we want to be able to look at Benford's Law for P-card. We've already looked at it for AP, so let's go run Benford's Law for the webcast on the transaction amount. We can see the general conformity again for it. And if we look at the first 2 digits, we're going to see that we have basically many of the same categories. We do have, however, with 20 and 21 and 30 and no 75, we have a few differences. So finally what we're going to do is we're going to come over to the APP card matches that we found, and what we want to do is we want to have a Benford rating for it. So we're going to come and append a field called the Benford rating, and we're going to give it another formula. Now this is going to be this complicated formula here. But basically it's the same thing as what we did before, but what we did is we have a complex if statement for invoice AP, where we're going to do exactly what we did with the duplicates. We're going to add a second one where we do the same kind of stuff for the transaction amounts for P-card, where you can see we varied the 20, 21, and 30 in place of the 20, 30, and 75, where the suspicious one, the highly suspicious, gives a value of 2, suspicious a value of 1, and everything else is 0. And we've employed the dollar value of 10 for our materiality threshold in this case. We've nested the results of these 2 complex ifs in a max function, so we can conservatively rank something that's a 1 in P-card and a 2 in AP as a 2 overall in our approach here. So we can get our Benford rating like so, and as before, we can now prioritize our search for which items we want to look at first, based on the ones that have that are in suspicious bins in Benford's Law. All right. So moving past those sets of tests, we can look at a few other tests as well. The last two digits test in IDEA is useful for detecting number invention, and it's looking at usually the decimals, 0.00, 0.01 to 0.99, and it expects those decimals to be evenly distributed, with each one occurring about 1% of the time. And this is typically good for inventory testing, and it's always important to note that AP invoices always show a bias of around the 0.00. With summation is a good way of being able to do first two digits test again, but using sums instead of counts, so that excessively large numbers can be found that may be driving the data from a material perspective. So this can be used to sometimes detect bias in different bins than the first two digits test. And we expect sums for each bin to be roughly equal. In IDEA, for our AP, we can come and look at our Benford's Law, and we can see where the last two digits test, again, has way too many zeros, but it looks to have an expectation that's pretty constant throughout. The summation test, again, could be used to identify other areas, such as the first two digits of 11, 12, 13, 24. There could be additional two-digit digits that you could incorporate when doing your Benford rating. So if by identifying 161 is not enough, you could, in addition to altering the materiality threshold, you could go and alter the formula to be able to include additional digits besides the ones found in the first two digits test with anything that happened to be identified in the summation test. Our final test in Benford's Law to discuss briefly is the second order test. The second order test always looks like this, or it should. This is where we have big spikes at the 10, 20, 30, and 40, 50. These are called prime digits in this test, and the others, those are called minor digits. So where the first two are 11 through 19, 21 through 22. And what the second order test does is it's really good for, again, that health check kind of thing. If it doesn't follow this pattern and you get, big spikes at 90, or you have spikes up on the smaller ones in between, then it indicates that there's something wrong somewhere. And the thing about the second digit test is, the second order test, is that it's very low on false positives. So if it indicates that something is wrong, you can bet that something is probably really wrong. But basically, the way that calculates things is it looks at the differences between amounts that have been ranked or sorted from smallest to largest, and groups them into bins. Differences of 0 are ignored. And what we do is we take all those differences and multiply them by 1,000 to get the first two digits. So penny differences become 10. And that explains, for example, why the 10 bin is so much larger than the others, and the same for differences of 2 cents. Those would go in the 20 bin. Finally, here we have what the kinds of things that define conforming populations for Benford's Law. You have a set of numbers that conforms closely will form a Benford set. We're going to look at the criteria that numbers that should describe sizes of similar phenomena, facts or events, things such as being charged by invoices and things of that nature. Numbers should have no built-in hard minimums or maximums. Numbers should not be assigned numbers, labels, ID numbers, or and things of that nature. There should be more small amounts than large amounts. And for procurement, inventory, and revenue data sets, they should conform if they're of high value and wide ranging. So these would be like your PO, invoice, good for receipt, and your sales invoices when the sales dollar amounts are not invented. Finally, non-conforming populations. So examples for of AR prices that may from tiered pricing structures, such as the cable company, ticket prices, software, where automation charges a particular amount for a license of software, and you tend to get multiples of that when invoiced. And because these come from tiered pricing structures, where ticket prices, for example, you pay a general price for 4 seats and a general price for nosebleed seats, those are all tiered and chosen in a particular fashion and aren't very natural, so they don't conform. Football scores, zip codes, phone numbers, bank account numbers, social security numbers, and license plate numbers are all examples of things that are more as much labels as they are numbers. And finally, we have salary survey numbers, where again we want no minimums or maximums, and a lot of times when you survey salaries, you can't put a cap at the high end, and maybe a cap at the low end as well. Briefly, just wanted to mention that we have, the references for this presentation came from Mark Negrini with his forensic analytics and digital analysis using Benfords Law. And that is what I had to show. Let me see if I can pull up the questions. I have a question for how big a population do you need for Benfords Law to apply? Well, you'd like to have it about 1,000, which could maybe get away with a little less than that. But the bigger the population, the better. And you at least need to have numbers that get up into the 4-digit range. So $1,000 or higher is typically the rule of thumb for what a population needs to have. If it only goes up through 999, it probably will not be any good. That's the one question I saw. Anything else?
I don't see anything else, Kurt.
Okay.
If you have questions, Kurt's information's on the screen. You can always reach out to us directly after the fact if you think of anything. And that's what we got. Thank you so much for joining us. And thank you, Kurt, for sharing with us.
All right. Thank you, everyone.
Have a great day.